Picture the crinkle of a chips packet. The shine, the snap, the promise of something tasty inside. Looks light, ordinary, and harmless, right? But this little packet is actually a fortress, built upon layers and layers of plastic. Sometimes even a thin sheet of aluminium, all packed tight, so no air, moisture, or light can sneak in and spoil what's inside.
Now, here's a twist. What makes it perfect for the food makes it a nightmare for the planet. These layers are bonded so tightly that they refuse to come apart, and that's exactly why recycling them isn't simple. In India, these fall under category 3 of the EPR rules, multi-layered packaging that we use daily.
So where does the story begin?
It begins right at the bin. How packets are collected and sorted decides their fate. One wrong mix and when the best technology can't recover them. So let's explore this topic further in the video.
Let's talk about a friend we all have but probably shouldn't. It's everywhere. In our bags, our hostels, our cafeterias, and even our pens. Yes, I'm talking about plastic. The one that never leaves. Literally. On a campus alone, we generate a hidden mountain of plastic every day.
Thank you so much, sir. आपने हमें टाइम दिया. So हमारा first question is कि थापर में कितना dry waste collect होता है?
थापर में अप्रॉक्स एक दिन में 2 टन ऑफ वेस्ट जो ड्राई वेस्ट कलेक्ट होता है.
और सर इसमें कितना वेस्ट प्लास्टिक है और कितना MLP है?
एक्चुअली टोटल 2 टन में से 50% जो कलर पेपर प्रोडक्ट्स टाइप होता है और 400 kg जो है प्लास्टिक वेस्ट है और 70 kg अप्रॉक्स डेली का MLP होता है.
सर इस सारे वेस्ट को कलेक्शन करने का क्या प्रोसेस है?
इस कलेक्शन के लिए हमने 3 रूट प्लान्स बना रखे हैं. डिफरेंट व्हीकल्स हैं हमारे पास. ट्रैक्टर है जो हॉस्टल्स करता है सभी, और एक मैनुअल ट्राईसाइकिल है जो एडमिन एरिया फूड आउटलेट्स देखते हैं उधर, और एक ऑटो ट्राईसाइकिल है जो हाउस होल्ड्स की कलेक्शन करता है.
और सर जब ये सारा वेस्ट कलेक्ट हो जाता है और MRF फैसिलिटी पे आ जाता है, उसके बाद क्या प्रोसेस फॉलो होता है?
सारा वेस्ट MRF पे आने के बाद उसका प्रॉपर वेइंग होता है, कितना वेस्ट डेली कलेक्ट हुआ, फिर सॉर्टिंग का कितना हुआ, उसमें कौन सी कैटेगरी बनी, और टोटल हमारे पास 19 कैटेगरीज हैं जो फर्दर हम उसको सेग्रीगेट करके स्टोर करने के बाद एग्रीगेटर को देते हैं रिसाइकलिंग के लिए.
The challenge we face with plastic isn't just unsightly litter, it is the visible debris that clogs our drains and pollutes our soil, breaking down into tiny particles called microplastics. These tiny invaders contaminate our food, water, and air, ending up inside our bodies. The pollution has immediate and tragic consequences for the wildlife as well, killing and injuring those who ingest it. Furthermore, every piece of plastic we improperly burn or dump releases toxic gases, fueling to respiratory issues and a release of greenhouse gases in the atmosphere.
One of the biggest challenges in recycling plastics is correctly identifying and separating the different types of plastic, especially multi-layer films that look similar but contain different materials. Traditional sorting is slow, error-prone, and can't handle the huge volumes of waste we generate every day.
Digital sorting methods use artificial intelligence and computer vision to automatically detect plastics based upon their appearance, texture, and sometimes even their chemical signatures. These systems are much faster and much more accurate than manual sorting, leading to higher, cleaner recycling streams and higher quality recycled products. Bringing a small part of this technology into our campus project shows how universities can contribute to waste management, research, and sustainability.
Hello and welcome to my plastic classifier machine learning model using Google Teachable Machine. So this machine learning model classifies plastics on the basis of HDPE, PET, and multi-layer plastics. Let me show you. So I here have a plastic bottle which it classifies as a PET. Next is serum bottle which it classifies as an HDPE. Finally, I have a chips packet which it classifies as a multi-layer plastic. So this shows the power of AI and machine learning in digital sorting, which can easily automate the recycling process to tackle the problem of multi-layer plastic waste. Thank you.
MLP waste is collected, lightly cleaned, shredded, and heated in pyrolysis reactor at 350 to 500 degrees Celsius without oxygen. The plastics break down into vapors that become solid tar that can be reused, pyrolysis oil, and fuels that can be used in the system. The emission controls keep the process safe.
Pyrolysis helps India deal with hard-to-recycle MLPs by turning them into useful oil, gas and car instead of dumping them into landfills. It supports our country's shift towards chemical recycling.
Harper generates around 700 tons of dry waste every year, and a large part of it is multi-layered plastics which cannot be recycled mechanically. Instead of dumping them, they can be safely used in brick kilns. These kilns operate at around 900 to 1100 degrees Celsius, completely breaking down MLP waste and using their high calorific value as fuel. Each brick consumes about 8 to 10 grams of MLP waste, replacing nearly 25% of coal and saving costs. This method prevents open burning and reduces landfill waste. However, strict emission control is required. With over 2,500 kilns in Punjab, this method has huge potential for sustainable development and energy.
While chemical recycling holds a massive potential, what if we could use multi-layer plastic today on a massive scale? The answer is
as follows. The challenge with NFPs is their complex group structure, but what if we could turn the design flaw into structural advantage? This is where plastic road construction comes in, a proven scalable solution pioneered globally, especially in India.
The process is remarkably simple. We take shredded multi-layer plastic, mix it with hot aggregates and let the plastic melt to form a superior coating. We call this dry process.
The roads built this way are 40 to 50% more durable and significantly resist water damage and pothole formation. Usually, every kilometer saves tons of carbon dioxide and significant amount of plastic waste from landfills and incinerations.
We are not just getting rid of the waste, we are upgrading our infrastructure using just 3 to 8% of MLP by weight of bitumen, transforming a chronic waste problem to a material engineering solution.
Our strategy to campus plastic waste is built upon innovation, practicality, and visibility. First, our infrastructure solutions include plastic roads and brick kiln recycling. These provide immediate and visible community impact. By utilizing campuses' existing infrastructure facilities, we can build better roads and durable pathways. This process demands collaboration and it is highly scalable, starting small from building better pathways and scaling it big to major road repairs.
Second, the on-site pyrolysis unit is an educational and practical powerhouse. We convert a consistent waste stream into valuable resources like pyrolysis, oil and gas. This innovative system, when scaled correctly, establishes a well-sustained circular economy and serves as an important material for our students.
Finally, we have a layered approach to sorting innovations. Mechanical sorting is immediately practical. We deploy bins and other equipment campus-wide to reduce contamination and improve the overall recycling rates. We take this one step further with digital sorting, utilizing student tech expertise to pilot AI-enabled bins and sensors. This turns waste management into a cutting-edge innovation challenge, generating valuable data and improving the overall scalability. These three practical pillars produce tangible benefits for us, our campus, and our environment.
Looking forward, we can pilot several new cutting-edge technologies on campus to tackle the problem of multi-layer plastic waste, meanwhile providing students with real research experience.
First, enzymatic recycling. Our environmental and biotech departments can explore enzymes like polyester hydrolysis to break down multi-layer plastics in lab-scale experiments, thereby making recycling more eco-friendly and green.
Next is the cool one, smart packaging. Students can design different digital watermarks for different types of plastics to allow easy automated recycling. This blends sustainability design with computer vision.
Then, our chemical engineering labs can also test solvent techniques like scrap to recover polymers safely on a miniature scale.
Lastly, with the blend of polymer science and packaging design, students can experiment with bio-based dye layers to rethink product design from the very start.
As engineering students, we recognize that the multi-layered plastic waste currently does not have a recyclable solution. For that, we need an innovative approach. Our project focuses just on that. Our project focuses that if we collect the campus waste and then segregate into different parts, we can use it to feed into different advanced recycling technologies. Moreover, we can use it as industrial applications such as road construction, brick kilns, chemical, automotive, and electrical industries.
By implementing digital tracking systems and awareness campaigns at TIET, we can bridge the gap between waste generation and sustainable end-use pathways. Future innovations in chemical recycling, AI-powered sorting systems, and blockchain-based circular economy models will empower students like us to transform plastic waste into valuable resources. This student-led initiative proves that technological innovation and environmental responsibility can converge, creating scalable ways that can help both our society and campus community.